Let's talk about isomerism in coordination compounds. So when we say isomers, so let's define isomers first. So isomers are compounds that have the same chemical formulas but different molecular structures and properties. Okay, so as we go along the different types of isomers that we observe in coordination compounds, you will slowly see what isomers mean. Okay. So in coordination compounds, there are two types of isomerism. So we have structural isomerism. So you have structural isomers. So they have the same chemical formula, but they differ in the way ligands are bonded to the metal center and through which atoms. So I will give some examples in a short while. And we have stereoisomerism. So there are stereoisomers. They have the same number and types of ligands. They have the same modes of attachments. How each atom is bonded to the other atom is the same. But they differ in the way in which the ligands occupy the three-dimensional space around your metal center. That's your stereoisomers. So now let's go first to structural isomerism. So there are three subtypes of structural isomerism. First is the ionization isomerism. So for us to understand what ionization isomerism is, we see here an example. Okay. So what do you observe? Okay. So notice that in the first example here in letter A, one of the ligands is sulfate and the anion of your compound is chloride. But in the second example, chloride is a ligand and the anion of the whole compound is sulfate. So this is ionization isomerism. So you see here that the difference is that your anion is either part of the complex or it's the ion that neutralizes the charge of the complex. That is ionization isomerism. Okay? So if you look at the composition, you have one chromium, one chlorine, you have 5 nitrogens, 15 hydrogens, 1 sulfur, 4 oxygens. It has the same, both of them have the same composition, both same elements, same number of elements, but they differ in the way your ligands attach or your ion. So is the ion part of the complex or is the ion the one that neutralizes the charge of the complex? That's your ionization isomerism. The next type of structural isomerism is coordination isomerism. So here, this usually takes place if both cation and anion are complexes. And what happens is that they just switch ligands with each other. That's your coordination isomerism. So here you see, you have the ammonia ligands attached to cobalt and the cyanide ligands attached to chromium. But in its coordination isomer, it's the chromium metal to which your ammonia molecules are attached and your cyanide ligands are attached to the cobalt metal center. Okay, so this is coordination isomerism. So these two compounds are coordination isomers. Next type of structural isomerism is linkage isomerism. So this is displayed by ligands that can attach through several atoms. What does that mean? For example, nitrite, NO2 minus. So your nitrite ion can attach to a metal center via the nitrogen atom as we see here, or it can also attach via one of the oxygen atoms as we see here. Okay, so this is linkage isomerism. So these two compounds are linkage isomers. Now, to distinguish the two in their names, so we know that the ligand name of nitrite is nitrito. But to distinguish the linkage, so we use nitrito N if the attachment is through the nitrogen atom, and we write nitrito O if the attachment is through the oxygen atom. And then in the chemical formula, we write NO2 if it is nitrogen that is attached, or ONO if it is the oxygen that is attached to the metal center. So this is linkage isomerism. So you see here in structural isomerism, the attachment, the way the ligands and the metal centers are attached to each other, that's how they differ. The composition of both compounds are the same, but the way the ligands are attached to the metal center differ. That's your structural isomerism, which is different from stereoisomerism. But I have one more slide here on linkage isomerism. So naming linkage isomers. So I've already shown nitrite. Okay, other typical monodentate ligands that can display linkage isomerism are your thiocyanate ion. So that's SCN minus. So it can bond via the sulfur atom. So it can bond via the sulfur atom, or it can bond via the nitrogen atom. So if it bonds via the sulfur, then you use thiocyanato. But if it bonds via the nitrogen, you write isothiocyanato. Another monodentate ligand that can display linkage isomerism is cyanate, which is OCN minus. So if it attaches via the oxygen, then the name is cyanato. If it attaches via the nitrogen, the name is isocyanato. So here we see an example of linkage isomers. So the ligand is attached via nitrogen, so that's isothiocyanato. Here, the ligand is attached via the sulfur, so it's simply thiocyanato. Okay? So again, when we talk about structural isomers, it's the way your ligands are attached to your metal center. So they differ with how they attach to the metal center. That is different from stereoisomerism, because in stereoisomerism, the way your ligands attach are the same. It's just the orientation in three-dimensional space that differs. Okay, so we will discuss two types of stereoisomerism. The first one is geometric isomerism. So this one is due to the positions of the ligands. So it's the position. The mode of attachment is still the same. It's just the position of the ligands that differ. So for example, if we consider a square planar structure, okay, for example, we have a platinum center, and the ligands, you have 1 chloride and 3 ammonia molecules. Now, this doesn't generate any isomerism. So you only have one compound with this structure, because regardless of the position of your chloride ion, it will still be the same compound, right? But if we introduce, or if we replace one of the ammonia molecules with another chloride ion, then we generate isomerism here. Why? So if this is the first chloride ion, so this is the first chloride ion, the second chloride ion that will replace an ammonia molecule can be placed here or here. And these are two different compounds. So the attachments are the same. It's the same. You have two chloride ligands attached, and you have two ammonia molecules attached, but the positions are different. And this difference creates two isomers. These are different compounds, so they have different properties. So to distinguish between the two, we use the prefixes cis and trans. So cis means same. That means the second chloride ion is on the same side as the first chloride ion. But actually, in reality, we don't have this order of the attachment of your ligands. So basically, when you see the prefix cis, it means that the two ligands are on the same side. And we use the prefix trans if the ligands are opposite to each other. Okay, so here we see a three-dimensional rendition of the structure of this molecule. So you see here the two chlorine ligands and the two ammonia ligands that are on the same sides. So that is your cis isomer. And here you see your chloride ligands and your ammonia ligands opposite each other. So that's your trans isomer. Okay. Now, if this complex is composed of 3 chloride ligands and 1 ammonia molecules, then there's no isomerism because it's the same case as this one. So regardless wherever you place your ammonia, all positions are equal to each other. So you get the same molecule. So there's no isomer generated if this is the case. Okay. Now, this is for square planar. Okay. So there is another geometric isomerism displayed by octahedral complexes, or those complexes with a coordination number of 6. So if you recall, if the coordination number is 6, the structure is described as octahedral. And aside from cis-trans, so in octahedral, you can also observe the cis-trans isomerism, such as here, you have 2 chloride ligands and 4 ammonia ligands. If your chloride is found on the same side, then that is your cis isomer. But if the 2 chloride ligands are opposite to each other, so their positions in the complex are opposite to each other, then that's your trans isomer. Now, if we have another chloride ligand, so that means we have 3 chloride and 3 ammonia ligands, then there is also another type of isomer because, okay, assuming that we start with the cis, okay, with the cis isomer, okay, the third chloride ligand can be introduced to what is called the axial position. So the axial position is this one and this one. You have 2 axial positions and 4 equatorial or meridial positions. Okay? So you have the axis here of your octahedral structure. So you have 2 axial positions and 4 equatorial or meridial positions. So if we start with the cis isomer, your third chloride ligand can be placed in an axial position such as this one, or it can be placed in a meridial or equatorial position such as this one. So you create another pair of isomers, another pair of geometric isomers. So for this one, the prefixes that we use are the fac and the mer. So fac is short for facial. Why facial? Because if you notice, if we place the third chloride ligand on an axial position, the 3 chloride ligands are on the vertices of one face of your octahedral structure. Okay? Because if you imagine, there are actually 6, that's 1, 2, 3, no, 8 faces. That's why it's called octahedral, because there are 8 faces in this shape. Let me just look for my mouse. There you go. There are 8 faces here. So that's 1. There's the other 1, 2, 3, 4. So it's like a pyramid with a square base. And then you have another pyramid with a square base that is inverted. So there are 8 faces in your octahedral. So FAC is for facial because the 3 ligands are the vertices of one face of your octahedral structure. Now this one, MER is for meridial because you have the three ligands on the meridial or equatorial position in your octahedral structure. Okay? So again, in the square planar structure, you only have the cis-trans isomerism, or that is a type of geometric isomerism. In octahedral, you have the cis-trans as well, and the FAC-MER isomerism. Okay, so these are geometric isomers. These two are geometric isomers. These two are geometric isomers of each other as well. Okay, now, based on what we just learned, let's look at this example before we discuss the final type of stereoisomerism. So, what type of isomerism is exhibited by, let's try to name this, triamine chlorooxalato cobalt 3. Triamine chlorooxalato cobalt 3. So this is a neutral complex. So it's asking for the type of isomerism that we find in this neutral complex. And for us to know that isomerism, okay, for sure, it's not structural isomerism, right? Because if it's structural isomerism, then we should be given a pair, right? Because they always come in pairs. Yeah. So this is, most likely this is geometric isomerism. First, let's identify the coordination number so that we can decide whether we will consider square planar or octahedral. So what is the coordination number? We have 1 chloride, 1 oxalate. So that's C2O42 minus, and 3 ammonia. Oxalate is a bidentate ligand, so it has 2 points of attachment. 1 point of attachment, 2 points of attachment times 1. 1 point of attachment times 3. That gives us 6 points of attachment. So the coordination number is 6. So the structure is octahedral. So next, we have to ask ourselves, is it a cis-trans isomerism or is it a FAC-MER isomerism? So let's try to draw that. Remember, so you have the equatorial positions and the axial. Your bidentate ligands should always attach on one side. So this is the attachment of your oxalate. And you have 2 oxalate. No, only one. Only one oxalate. Okay, only one oxalate. And then I have 1 chloro. So if I place my chloro here, that means my ammonia ligands are here. And this is a FAC. This is a FAC isomer, right? This is a FAC isomer because you have there the vertices of one face. So that means we can draw a MER isomer for this complex. So how will the MER isomer look like? So again, these are the equatorial positions and the axial. That means the 3 ammonia ligands must be in equatorial positions. And then, okay, your chlorine can still be in the same position, but your oxalate is attached this way. So one attachment is in the equatorial position and the other attachment is in an axial position. So we have geometric isomerism, to be specific, Fachmer isomerism. Okay, that's the answer. So now let's go to the last type of isomerism, which is optical isomerism. So this has something to do with mirror images. Okay, so if we look at our hands, the left and the right, they are mirror images of each other, right? Mirror images. But they are not superimposable, which means if I superimpose my two hands, they do not overlap. There's a difference, right? So in chemistry, we also have such structures. So there are molecules that are mirror images of each other, but they are non-superimposable, such as shown here. And this is very prominent if you have a central atom and the surrounding atoms are different. That's why you have their different colors, yellow, red, purple, and green. So if you notice here, these two are mirror images of each other, but they are non-superimposable, which means they are two different molecules. So the term used to describe such structures are called enantiomers. So enantiomers are described as chiral compounds. As we shall see later on, we will see later on kung anong ibig sabihin ng chiral. Now, for now, you just have to understand enantiomers. So enantiomers are non-superimposable mirror images of each other. Okay? So, what does it have to do with optical isomerism? So from the name, optical, right? So it has something to do with light. Okay? So enantiomers, unlike the previous isomers that we have discussed, enantiomers, so you have two molecules, right? Same attachment of atoms, but they are mirror images, non-superimposable. So they are two different molecules. But enantiomers have the same properties, except a few. In particular, their optical activities. So they have the same properties. For example, they have the same melting points. Okay? Enantiomers have the same melting points, for example, but they interact with light differently. So this isomer interacts light in a different way. The other enantiomer interacts with light in a different manner. Now, what is this interaction? So it has something to do with the rotation of polarized light. Okay, so we know that any source of light is unpolarized. So it means you have light in infinite orientations. So if you imagine, diba, light is a wave. So you have wave at 0 degrees, 1 degree, 2 degrees, and so on. That's unpolarized light as shown in this schematic. Okay, so if you polarize this, so you choose a certain orientation of your light, so you filter it. Okay, so once you have your polarized light, you allow it to interact with your optically active sample. Okay, so this interaction of polarized light with your optically active sample has a consequence. What is the consequence? Your polarized light will be rotated to a certain angle. So if you start with a polarized light that is at 90 degrees, so it's vertical like this, it will be rotated, for example, positive 10 degrees. So if it's positive, that should be to the left or counterclockwise. Or it can rotate this polarized light 30 degrees clockwise. That's the effect of the interaction of your polarized light with an optically active sample. Now, the thing is, with enantiomers, their behavior with polarized light are opposite, which means, so if I have enantiomers, right, non-superimposable mirror images, enantiomer A will, say, rotate polarized light 10 degrees counterclockwise, but this enantiomer will rotate polarized light 10 degrees clockwise. So they have different interactions with polarized light. Okay, that's what we call optical activity. And this has something to do with the term chiral. So when you see the term chiral, it means that that molecule is optically active. That's why enantiomers are described as chiral compounds, because they are optically active. Now, how is it displayed in coordination compounds? So here, this is typically displayed by polydentate ligands. So here we see a cobalt center, and we have 3 ethylene diamine ligands. So recall, ethylene diamine is attached via 2 points. So it's a bidentate ligand. So you have one here, and another one here. If you look at the mirror image of this one, so if you imagine, okay, there's one point of attachment and then the second point of attachment. Okay. Then you have here in another axial position, your second ligand, first attachment and second attachment. And then you have this third ligand with the 2 points of attachment. Then you have the mirror image. They are non-superimposable. Okay? This might be difficult to appreciate because we are looking on a 2-dimensional plane. But you can think of this as the blades of your electric fan. Okay? If you look at the blades of your electric fan, they are not straight, right? So they are angled to some degree relative to your center, relative to the center of your electric fan. So you can imagine it that way. So this is these are the blades of your electric fan. Okay. And if you look at it, if you consider, if you blow through one of them, they will rotate in a different direction, in some direction, while the other one will rotate in the opposite direction. Okay. So this is your optical isomerism. Again, it is displayed often by polydentate ligands. Now, there is not much to say further about optical isomerism, but just consider this class. If you have a mixture of your enantiomers, so the 2 enantiomers, if you have a mixture containing equal amounts of the 2, they cancel each other's optical activity, right? Such mixture is called racemic mixture. So a racemic mixture contains your optical isomers of equal proportions. They cancel each other out, so a racemic mixture will not display any optical activity. But, for example, if you have 5% more of your isomer B, then it can still display optical activity, but hindi na yung full na 10 degrees. Okay, because some of that is again canceled out by the presence of the other enantiomer. Okay, so when you want to separate the 2 enantiomers in a racemic mixture, we call that process resolution. Okay, so if you want to isolate only one enantiomer, then you can check its purity by looking at its optical activity. Is it completely rotating your polarized light by 10 degrees? If so, then you have a pure mixture of this enantiomer. But if it's not fully rotating by 10 degrees, then it means you have some of the enantiomer A present in that solution. So you have to further undergo resolution. Okay, so that's all about isomerism. So again, we have 5 types. Well, we have 2 general types, which is structural isomerism and geometric isomerism. Now, stereoisomerism, structural isomerism, and stereoisomerism. Under structural isomerism, you have ionization, coordination, and linkage isomerism. And under stereoisomerism, you have geometric isomerism and optical isomerism. So in the next video, we will be learning about bonding theories in coordination compounds, in particular the crystal field theory. So this is very important in understanding 2 properties of coordination compounds, which are their colors and their magnetic properties.